Okay, so the fourth gas law is what we call Gay-Lussac's law. Gay-Lussac was a famous French scientist who developed the next gas law that we're going to talk about, which is the ideal gas law. This guy was a really huge influence on the whole science of gas laws. And basically what he came up with was a variation of the combined gas law. And let's take a look as to what I mean by that. We said the combined gas law is P1V1 over T1 equals P2V2 over T2. Now, if the temperature is constant, then those two terms drop out because you have the same number on both sides of an equal sign on the same side of the fraction. They will cancel out. And that leaves you P1V1 equals P2V2. That is Boyle's law. And we said Boyle's law is at a constant temperature and that the pressure and volume are inversely related to each other. If we took the same idea, combined gas law, and we said that the pressure is constant, the P's will cancel out, and that leaves us V1 over T1 equals V2 over T2. That is Charles's law. And we stated Charles's law, it occurs when the pressure is constant. So if we go one bit farther with that, and we take the ideal gas law, the combined gas law, and have a constant volume, which has not been considered up to this point, we have the volumes canceling out to leave us P1 over T1 equals P2 over T2. And that is Gay-Lussac's quantitative law. That is the mathematical version of Gay-Lussac's law. The qualitative one is that the fact that when you have a situation like this that came from P equals some constant times T, that is a direct relationship. And that means in a direct relationship, as you change one variable in one direction, the other variable gets changed in the same direction. So that means as the pressure of a gas increases or decreases, its volume increases or decreases, depending on what you've done to gas. I gave two examples of this on the script. Let's take a look at them. First example, we have 25 liters of oxygen at STP. So that means T1 is 0 degrees Celsius or 273 K, and P1 is 1 atmosphere. But since the second pressure is 850 torr, we have to change that 1 atmosphere over to 760 torr so that we have the same pressure on both sides. And we're going to solve for T2. Now there's two ways to do this problem. The first way is by ignoring the volume because it's constant. We don't have to worry about it. P1 over T1 equals P2 over T2. And so we plug in the values that we got. 760 torr over 273 K equals 850 torr over T2. Again, this is a proportion, so we cross multiply. And it makes no difference which direction you go as long as you go numerator times denominator equals numerator times denominator. That gives you 760 torr times 2T equals 850 torr times 273K. And to get the T2 by itself, we divide by 760 torr. The torrs cancel out. Leaves us an answer of Kelvin at 305. Now, again, just like in Charles's law, we don't have Kelvin thermometers. You don't see Kelvin anyplace. You don't see them in the bank buildings or on top of the bank buildings where they have the temperature scale. They have, Fahrenheit and Celsius, no Kelvin. So we have to change it over to something that people can, in most of the world, can recognize. Not us, but the rest of the world. And so we subtract 273 to change that over to Celsius, and we get 32 degrees Celsius. That is the way I suggest. Don't have to do it this way. You could do it this way by using the combined gas law. In the combined gas law, we have P1V1 over T1 equals P2V2 over T2. Now we put in the 25 liters for both V1 and V2 because temperature does not change. So we cross multiply like we did before. Oh, and now we got this extra 25 liters in there. This is the same as what we had before, except we got 25 liters here, 25 liters here. And you get T2 by itself, we got to divide by both sides by this pair of numbers multiplying each other. And that means that 25 liters is found in both the numerator and denominator, and they will cancel out. torrs cancel out. So we're left with 850 times 273K over 760, which is exactly what we had in the first problem, giving us 305K minus 273 equals 32 degrees Celsius. Now, what I'm suggesting here is that if you're not sure what the gas law is, you can always go to the default one, which is the combined gas law, and plug in for the values there. That's fine, as long as you know what the other quantities are. If you're missing a variable, then you probably are in the wrong gas law. But the combined gas law will kind of make up for that misunderstanding. The second example I gave you gives you no volume. It says it's a constant volume, so we don't even consider using the second method. We just use the first method. First pressure is defined as 28.7 inches of mercury. The first temperature was negative 15 degrees Celsius, so we had to add 273 to that, get 258K. We're trying to find out the new pressure when the new temperature hikes up to 15 degrees Celsius, and when we add 273 to that, we get 288K. Plug in for Gay-Lussac's law, P1 over T1 equals P2 over T2. 28.7 inches of mercury times 288K equals P2 times 258K. And then we divide both sides by the 258K to get that by itself. And we end up 32.0 inches of mercury. So, that's basically the same idea. We're doing basically the same thing for all four gas laws. Getting the variables figured out with the correct labels, then we plug in for the variables in whatever gas law we're dealing with, and we're just doing basic proportional mathematics in order to solve the problem. And making sure that we have 3 sig figs in the answer, except for temperature. The temperature must be always round off the nearest whole number. And then we deal with our practice problems here. We have 5 practice problems again. Have fun.